So, good evening, everyone. Uh, Mainly my colleague. I'll be taking a test run for the tutorial or TA-ship of the Advanced Quantum Mechanics that is taken by the instructor Saurabh Basu from IIT Guwahati. So, I'll just solve a few questions here just for the test case, and from next week onwards, we will have proper classes of 1 hour. So let's begin with solving one of the first question that was given in week 0 assignment, that is finding the commutation relation of x and p, where x is a position operator. Okay, sorry about that. X is a position operator and p is a momentum operator. Okay, so while finding the commutation relation, so this is one of the fundamentals of the quantum mechanics, that a commutation relation between x and p is I h bar. This is mostly a given thing. But to find it out, what we do is we implement this commutator on wave function psi of x. Now, as we know, a commutator a comma b is defined as, so these are all operators. Sorry about that. A comma b is a b minus b a, and we are going to implement this onto the wave function psi of x. So we know that if x is operated on psi of x, we get psi x because that is x is the position of the wave function at when this x is operated, whereas p is defined as minus I h bar del by del x psi of x. So we are going to use these definitions, these three definitions, and we will find out the commutator x comma p equal to I h bar. Now let's first begin with the LHS here. So we have x p psi of x implementing. So we first open the commutator, that is we have xp minus px, and this is operating on psi of x. So let's see what happens when the first part operates on psi of x. So what we will have is x operator and minus I h bar del by del x psi of x, and for the second case we will have minus p x psi of x. Now x commutes with del by del x, and what we get is minus I h bar x operating on this derivative of psi x will give us psi x derivative, so this remains as it is, and we have a derivative operating here, it's h bar. Okay, it's getting quantum, minus I h bar del by del x operating on psi of x. So this gives us minus I h bar x del x psi of x plus first the derivative on x, and then we do derivative on the psi x. So what we will get is plus I h bar psi of x plus I h bar x psi of x del by del x psi of x. So first we took the derivative of x, and then we took the derivative of psi x, keeping x as it is. Now these two gets cancelled out, and what remains is x comma p psi of x equal to I h bar psi of x. So hence we get x comma p operators equal to I h bar. Okay. Now this is used all throughout the quantum mechanics. Everywhere you will find this commutative relation being used. Now moving on to the second question, we find out the commutator of x comma h, where h is a Hamiltonian for a free particle. So uh, for a free particle, you might have seen in your quantum mechanics 1 or 2 courses that for a free particle the Hamiltonian is given by minus p square by 2m, and there is no potential involved. And as we have seen in the previous question, that p operator can be defined as minus 1 by 2m I h bar del by del x whole square, right? And this can be further written as, so I square is minus 1 essentially, and we end up with getting, so minus into minus 1 is 1 minus h bar square by 2m del square, right, del x square. So this is the Hamiltonian operator that we will be operating on. But uh, you won't actually need this. So what we are going to do is we are going to use a trick. When you have a comma b c, let's say you have a multiplication of operators, then this relation, this can be written as uh, b a comma c plus a comma b c, and we are going to use this property to find out the commutators, because we know the commutation between x and p, so this property can be very useful here. So uh, let's find out what the result is. So when we have x comma h, we go through the procedure in a similar way as we have done in the first question, and what we get here is x comma p square by 2m minus acting on psi of x. Now the coefficients part, that is minus 1 by 2m, can be taken out because it doesn't really act, it always commutes, so we only consider the operators here, and what we are seeing here is 1 by 2m comes out x comma p square psi of x. Now this p square can be thought of as p dot p. Okay, this is two operators multiplying, so instead of b c we have b and b. So what we are going to do is minus 1 by 2m, we have p x comma p, and we have plus x comma p p psi of x. So okay, now there are two things. First, when x is operated on psi of x, we have x psi x, and when p is operated on psi of x, we have p psi x, that is the momentum at that point, momentum of the wave function. So here what we end up with is, so here p is operating first on psi of x, so we get a p psi of x. Here x comma p is operating on psi of x, which gives us I h bar psi of x that we have seen in the previous result, previous question, right? So what we have here is p I h bar psi of x plus x p, we have p psi of x. Now x comma p will act on psi of x, so we end up with I h bar p psi of x plus I h bar p psi of x, and the ultimate result, as you can see here, is x comma h psi of x equal to, we have twice, so these two are the same, we have minus 2 I h bar p by 2m psi of x, 2 cancels out, and taking out the psi of x, ultimately this commutator relation corresponds to minus h bar p by m. Since my colleague is superior to me, I'm pretty sure he won't have any doubts, and we can move on to the next question. Now, third question, we are going to find the dispersion relation for free particle. So dispersion relation essentially means that we are going to find the relation between the energy versus the wave vector, that is E versus K. Okay. Now for a for a free particle, what we already know, as we have seen in the previous question, is that the Hamiltonian H is equal to minus p square by 2m. So this is the only thing that is given to us. And as we have derived in the previous question, so that comes into the help now. So we had minus h square by 2m del square by del x square. Okay. Now to derive this relation, what we are going to do is we are going to use the Schrodinger equation. So we are already familiar with the Schrodinger. Okay, so we know in Schrodinger equation we have a Hamiltonian acting on a wave function gives us the energy of the wave function. This is so Hamiltonian operating on psi of x give us the energy of psi of x. So this is what we know from the Schrodinger equation. Now putting the Hamiltonian from here, what we get is minus h square by 2m del square by del x square psi of x equal to E psi of x. So taking these coefficient to the right side, we get del square by del x square psi of x equal to 2me by h bar square, there is a minus, psi of x. Now, most of you must be familiar with solving second order differential equations. So you might have seen something like you have d square of a equal to some constant d square of, let's say psi, let's keep it psi, equal to a psi, and then you do d square minus, you take, make it square, a square, psi equal to 0, you solve, you get d equal to plus minus a, something of that sort. You might have seen in your math methods courses the solving of second order differential equation. Now, using that same thing here, what we do, what we get is that the wave function psi of x can be written in the form a e to the power I kx plus b e to the power minus I kx. So this is, you can say, a general form of the wave function, an ansatz. And here the k essentially is your root over 2me by h square. Now you take the square of both sides. What you get is 2me by h bar square, and taking all the coefficient of e towards the right side, you get ek equal to h square k square by 2n. And this is the dispersion relation. You have energy and you have the wave vector. And in terms of omega, you can also write, so we know energy is usually written as h bar omega k, okay, where omega is the angular frequency, or this it's angular frequency. And in terms of that, you can write it as, so your omega k is essentially h bar k squared by 2n. This is dispersion relation in terms of omega. Okay, and so based on the dispersion relation, we have the next question, which is finding the expression for group and phase velocity. Okay, so this is not exactly related to the previous one. So, but this we can use this previously derived result as an example for this fourth question. So in order to find the expression for group and phase velocity, it's essentially for, let's say, for free particle, for the case of free particle. Now the group velocity, let's do with the phase velocity first. The phase velocity is usually, or it's defined as Vp equal to omega by k, where omega is the angular frequency that we saw, angular frequency of the wave, and k is the wave vector. Now for the free particle, we just derived that omega was h bar k square by 2m. So the phase velocity that we get here is essentially h bar k by 2m. And the group velocity is defined as d omega by dk. So this problem turns out to be pretty simple. We have h bar k square by 2m. So h bar k square by 2m, and we take the derivative, we end up with getting 2 h bar k by 2m h bar k by m. Now you can see that there is a factor of 2 missing in the phase velocity and the group velocity, and okay, so these are the expression for the phase velocity and group velocity for the case of, sorry, for the case of free particle. Now, going to the final question, we are going to find the expression for energy in a one-dimensional box of width A. So let's say have a box, the size is A, and let's say this is infinite potential. So V of x can be defined as infinite, 0, and infinite in three regions. So there is this, let's say this is 0, this is A. So when x is less than 0, it's infinite. When x is 0, A, it's 0. And otherwise, again, x greater than A, it's infinite. So the Hamiltonian that we get is something like minus p squared by 2m plus v of x. And you can write this in different regions. So in region 0 to A, H is essentially a free particle, whereas in everywhere else there is there can't be any possibility of the wave function. The wave function will just be 0 as H tends to infinity. In these cases there can't be any, yeah. So as H tends to infinity, there is no possibility of wave function being there. So what we end up in short is basically with the wave function that we have seen previously, that is a e to the power I kx plus b e to the power minus I kx. And as I said, that this is in the region 0 x a, and otherwise it's 0. That is for x greater than x less than 0 and x greater than a. Okay. Now, since a wave function has to be continuous, this is one of the fundamentals of quantum mechanics, that psi x has to be continuous. Sorry, not just psi x, but as well as differential first order derivative of psi x has to be continuous at every point. So what we are going to essentially do here is we are going to match at the boundary condition. So at x equal to 0, we know psi of x is essentially a plus b, psi of 0 is essentially a plus b, and psi prime of 0 is 0. Sorry, it's k I a minus b. Okay, I'll just do derivative of psi prime x. Sorry. So psi prime x is equals to I k a e to the power I k x minus I k b e to the power minus I k x. And at x equal to a, psi of a is equals to a e to the power I k a k a. Psi prime of a is I k a. Sorry, it's getting a bit congested here. minus I k e to the power minus I k a. I should move to the next page. And based on these four conditions, what we have is, firstly, at psi 0, the wave function is essentially 0 because of the infinite potential. We have a line. We have a plus b equal to 0, which means a equal to minus b. And we can do it just by the two conditions. For psi a is also 0, that means a e to the power I k a, and we can put b equal to minus a here, that is a minus a e to the power minus I k a is also equal to 0. So a e to the power I k a minus e to the power minus I k a is equal to 0. Since a cannot be 0, otherwise the wave function is always 0, we have the other part to be 0. A per I k a minus I k a equal to 0. You can divide by 2, and this essentially gives us sine of ka equal to 0. And you know sine can be 0 at 0, 2 pi, 4 pi, that is n pi. So we have the solution as n pi here. Now, in the previous part, we have seen the energy corresponding to k, right? Here you have seen how E is corresponds to K, that is 2me by h bar square. This, putting this here, we get root 2me by h bar square A equal to n pi. So taking square on both sides, we have h bar square A square n square by pi square. And we finally get the energy for a one dimension potential. Okay. And this is all for the test run case. Thank you.